And today we're going to be talking about modeling IoT workflows using IoT and serverless technologies. In terms of my background, I have an engineering background. I've worked as a software engineer before joining AWS. I've worked as a technical architect at AWS, and then because I want to share my knowledge with the developer community, I decided to start my own developer advocacy. So let's get started. The situation nowadays is that we have more and more connected devices. Different use cases, for example, connected homes or manufacturing or automotive, you name it. But the number of connected devices is actually reaching billions. Because devices are of different, exposed different constraints. We are dealing with embedded devices, which are very constrained, or with really powerful gateways. It's important to be able to uniformly remote manage these devices. In fact, for IoT, remote management is not just for efficiency purposes, but it is actually a necessity. So once you have your devices out there, as a device manufacturer, but also more as a product creator or product or a company that produces products that depend on IoT devices, what you don't want to do is be forced to send your technicians on field to actually roll firmware upgrades on your devices with a USB stick or crazy things like this. So it's really important to be able to do efficient remote management. Of course, this means that the expectations from remote management platforms are actually increasing more and more. So what this means is that distributed set of operations that need to be performed against devices are becoming more and more complex, and also need to be performed often outside of what happens on the device, because the device capabilities are not enough for tiny devices in particular. Also, you have to think about what happens when your devices need to reboot, for example, in the middle of a firmware update workflow, or what happens if the connectivity is actually intermittent and your device is not permanently connected to the internet. I mean, think of an elevator, for example. If you're monitoring elevators and they go to the garage, ground floor, or underground, you lose connectivity for a little bit. What should happen if the device is in the middle of a firmware upgrade as this happens? And of course, we're also talking about power grids. So in this session, I'm going to talk a bit more about what IoT workflows are and what the expectation and challenges are of workflow management systems for IoT. I'm also going to present 3 different approaches for modeling or designing IoT workflows, and then we're going to talk in detail about one particular approach. And you will see also an implementation, and if the internet connection works, I'm going to do a demo on about 100 simulated devices, and you will see how firmware upgrades are being performed on these simulators. So this is the last step. What I also want to say is that this solution focuses on moving away from the really deep technical details that usually happen at edge, right? So IoT edge protocols are extremely complex at times. So what we need is a solution that, on a higher level abstracts away from these complexities. So we're not going to go very deep into the low-level specifics of certain device management protocols at edge. For example, DR369 for routers, or SNMP, or anything based on CoAP, or anything WMM, and so on. We're not going to talk about that. Not so much anyways. So let's see what IoT device workflows really are. So throughout the life cycle of your devices, your device is actually going through multiple different kinds of workflows, right? From provisioning, which is onboarding your device with your own personal settings, right? So think about this onboarding flow as something that, from a user perspective, needs to be seamless, right? So you love to buy a device, plug it into power, plug it in, or configure it with Wi-Fi settings, or maybe not even do that, and you have it working. So, like for example, you buy an Apple TV device, you connect it, it actually retrieves everything about your profile, knows who you are, updates with your settings, and then suddenly you turn it on and it just works. So this is not a principle of just working. It is simple from a user perspective. However, behind the scenes, you're dealing with multiple different operations that are happening on device and outside of the device they call interactions with backend systems and so on. So that's actually what a workflow is. Other type of workflows where the device is in operation, for example, is putting device configuration over the air onto a device, or doing use cases like data collection, processing data in real time, any kind of data transformations, and other processes at the time. Of course, the in-operation workflows depend a lot on what you're doing with your device, so what your use case is. Maintenance is, of course, a lot about device management. So it's about over-the-air updates, security fixes, it's about bug fixing, it's about new firmware that is being released to your device, and other workflows like this. Of course, you can also do remote troubleshooting, which we are going to talk about later in more detail, to figure out what is wrong on a subset of your devices if you want to. When your device is being decommissioned, which is also very important for IoT manufacturers in particular, this is the process of removing the settings from your IoT device. And also workflow needs to happen behind the scenes because you have to first find out what you need to remove based on what type of user maybe your device is being used by. Then you have to interact with a bunch of other internal or external systems and reset the device allocation settings. So what all these workflows have in common is that they are complex. So operations need to happen on device and operations need to happen outside of the IoT devices. Complexity also comes from the fact that you need to cater uniformly for potentially a small microcontroller and a powerful gateway, right? So it's actually happening that the devices are not at the same time, right? So you have older generation of devices, you have newer generation of devices, so on and so forth. So you need to manage all of that remotely, ideally, under the same platform. The distributed execution is also causing the problem. And you also want to have possibly asynchronous communication with your device and also the other systems. So the best way to actually deal with this is by decomposing and simplifying your solution. And we're going to talk more about how. So this is the example that I was talking about with the fault troubleshooting, right? So imagine you have 500,000 devices, you run a firmware upgrade, and suddenly 20% of the code doesn't operate as desired. What you want to do is enable, for example, a deep inspection on those 20% devices and see what's going on and have them send data periodically a lot more than you would normally send data from those devices just to see where the problem is. So you enable this inspection, you receive data for a while, you store it, you analyze it, you go through this workflow, and let's say after 30 days, you want to disable that. So you will actually disable it, and this is how your workflow would, this is when your workflow would stop. So what are the challenges with what we're trying to achieve? Reliability is important in a workflow. Certain devices cannot deal with doing retries, for example, on the device. It's also sometimes impossible to, if you have to interact with other systems, sometimes you can't do it from your device because it's just too much effort to enable retries, enable error handling, and so on. If you have a really small device, this is not possible, right? So that the question comes, where does this workflow run, and how do you build it in an efficient way? Visibility and observability is another aspect, right? Because it's one thing what runs on one device, but if you're dealing with a workflow, you actually want to get observability, to get information onto the state on multiple devices, possibly your entire fleet. You also want your workflow implementation to be flexible. So if you add a new device model, you don't want to implement the entire workflow, ideally. And also if you want to support the new protocol, you also don't want to implement your entire workflow solution. And expressiveness is about adding more operations, right? So if your product manager comes in and says, hey, we want to add a new interaction or swap from system X to system Y inside our workflow, how much effort is this? So you want actually that effort to actually implement the new task or modify an existing task doesn't involve modifying tasks. Complexity is also coming from the fact that you're dealing on one side with different hardware providers and a hardware level or the application, the firmware that actually runs on the devices already needs to be compatible But we also are going to investing in distributed systems, right? So who is orchestrating your workflow? Do you want to have an standardized workflow, or do you want to have an implicit workflow inside your different ingredients? So from an expectation perspective, we would do a simple retrieve model, and we would say that on a basic level, you have observability operations that involve you interacting with the device. Now, these two operations are atomic, and of course, we need to ensure that there is levels of consistency and also that your device doesn't get bricked. But this is the basic level, right? The basic level is to have some code. If it's running in the cloud and indeed a lambda function or your internal within your running something on prem, but it's just really having a service interaction with the device and sending commands to the device. So basically, you should be implementing the device management protocol that device manufacturer or that device supports. So that's the basic level, right? Of course, you need to make sure that that your operations don't break your devices. Then the next level is how do you aggregate multiple operations, right? And how do you ensure that they perform a task? And making sure that the workflow is specifically defined. So flexible definition and execution, we talk about this. Also, you want to make sure that whatever you do and design is scalable. It doesn't work just on 10 devices or 100 devices, but it actually works hopefully, on millions of devices, if not even more. If you want to do some smart device management, ideally you will be able to target groups of devices for workflow execution. So you would execute your workflow as a minute, and you target, let's say, half of your fleet, for example, or you target based on smart queries, like what percentage of your fleet is in Europe, what percentage of your fleet is in the US. So maybe you want to perform updates and roll them out to the US devices first, right? This kind of operation, this is what would be the design intelligence layer into your workflow. Of course, also metrics is another aspect. You need to know that your workflow execution as a whole works successfully, and you also need to know what tasks were successful and what tasks failed. And this needs to happen at fleet level, not at individual device level. So it's the approaches to design. So we're always looking or thinking about how one would design such a solution. The criteria for establishing the architecture would be where the workflow is located and what drives the workflow, right? So you could have a workflow solution that is driven by device. I mean, if that's a smart thing to do, I don't know, depends on the use case, we will look later. You could also have an embedded solution, maybe cloud managed, maybe non-cloud managed, right? But you could write your workflow whereby only you know it's a workflow, because the workflow is actually happening inside the code. It's not, you don't have explicit orchestration, you have an embedded workflow, and every single component in your system performs the task that is part of the workflow. But you can also do unserverlized and cloud managed workflow execution. And this is what we're going to focus on today. We're going to learn more about externalizing your workflow orchestration. So let's see. So, briefly about the device-driven workflow management, right? So, in this case, with the device-driven workflow management, you still have a scheduler which schedules the jobs, so it schedules the execution of your workflow. And then you have the device management component, which starts your workflow. But everything that happens as part of your workflow, including interactions with other systems, is done on the device. If you have a powerful gateway, then definitely this can work. Your device can, keep track of state, and you also keep track of state at task level, or you can do it at workflow level. So essentially it can work, but of course, doesn't work for those big devices, that's obvious. It also works only if you have an efficient over-the-air mechanism in place. Right, so if you have a mechanism whereby you can update your devices over the air 10 times a day without any compliments, your devices are powerful enough, then that's fine, right? Also, if your devices need to interact with other devices that are in the network, and your workflow doesn't involve interactions with backend services and third-party providers, then of course you can do this. If your hardware types actually change also infrequently, they don't have to cater for multiple hardware types, so that's fine. However, the limitation is included within the fact identification. And generally, IoT solutions are attempting as much as possible to move away from a fat edge and do more logic into backend services, while there is still not our services. Of course, there's much flexibility, and there is much flexibility for constrained devices, and all the SLA implementation, the rate limiting, the interactions in the certain system can be done on the device. So moving on, and this is something that actually I see quite a lot working with customers in these days, right? So they've got workflows, and those workflows are actually embedded. And I'm not here to see a PP page that describes their IoT solution for firmware upgrades. And reading through that PP page, you actually can see it's a workflow that's happening. But when you look exactly in the code, you see just a bunch of microservices, and that's basically it. So this is the case where you have a chemical scheduler that starts the workflow, and that it has different components, microservices, different databases, different external systems. Every single component in this architecture would be performing its own functionality. At one point, it would be talking to the device management system as well. But you can't tell from looking at this that it is actually a workflow. It just looks like a solution. Of course, this is not very hard to implement, depending on the scale that you need. So if you are targeting, let's say, 100,000 devices or 200,000 devices, you could potentially do this. For small island fleets, which where actually you have some workflows, you don't run them very often, right? So I still work with customers who do an OTA to their device maybe once every 6 months or once every 3 months. So when you do that, then maybe it works. If you've got also device-level workflows, and you combine device-level workflows with this kind of solution, it also could work. But you run the risk of actually implementing pipe coupling, and then the complexity is growing quite fast. And of course, they're not so flexible. When you're trying to add a new, let's say, operational task in your workflow, it really affects your entire system, right? So you might need to re-architect just to build a new operation. So it's quite destructive, requires a lot of testing, there can be a lot of regression happening. So maybe also not the best approach, but of course eventually in this case. And the third solution, which is what I will talk about today in detail, is an externalized cloud-managed workflow management and execution. So when you part your workflow explicitly defined, you have again your scheduler, and then you have components that is really designed to orchestrate your workflow. So you can have multiple workflows. So this component can actually orchestrate multiple workflows. You can define them, so you have workflow definition and the workflow execution. And also you can track state, right? So if the state here is not the state for one device or for one workflow. This is centralized state management for all the devices. So for your environment. Of course, in this case, if you want to reply, you can reply at task level. If you want to configure inputs and outputs, you can really do it in every step separately, right? So you can reply, for example, just step N instead of requiring to reply a workflow and something goes wrong. It's also easy to fan out, right? And we would simply say wrong, so you would basically fan out in multiple instances of this workflow execution. Emulation of metrics, again, you will don't worry about your system at all. This network architecture is what we're going to go and move forward into. It can be expensive if you have to build this in-house and you have to run it, make it scalable for, 10 million devices, for example, it would be expensive. And of course, if you're operating small fleets, again, it might not make any sense. So let's do a state machine study, and we probably would have figured this out by now, even that state machines have been around and have been used, also by embedded engineers, but also for backend services. They are an efficient way to model workflows, right? So another mechanism to break down complexity. You separate the different units of functionality. You can retry them, you can execute them in parallel, you can execute them sequentially. So it is a way to model system behavior. You can also have variable state machines, and using this sort of state machine concept helps also to loosen the temporal bounding, right? So if you need to wait for a task your other tasks that don't need to wait for that particular task to finish and continue executing while you're waiting for a result or, let's say, an asynchronous execution from your device, which is actually quite nice. So if we look at our previous architecture, a generic workflow with this would be like this, right? So you have an orchestrator, you have again your processing, your topical processing and scheduling, you have an orchestrator and multiple workflow definitions which are separated, and then here is your state machine. So your state machine is defined in the workflow definition and instantiated by your orchestrator, and you got one per instances random of your state machine. And again, each of the tasks can interact with different pieces of business logic, including the device management component that can interact with your IT devices. So now, in order to exemplify this, I'm going to talk about how you can model, based on this workflow and state machine definitions, how you can model a firmware upgrade, right? So the firmware upgrade we're going to talk about is tailored for devices that are constrained, and also where your device is capable to do AP switching, right? So you have, at the same time on your device, you can have two different versions of your firmware, and if you want to upgrade, you send the message, and the device will download the new firmware, the old firmware will still remain active, and then the device will try to boot in the new firmware. If it works to boot in the new firmware, then it's all fine. If not, it will continue with the old firmware. So this is what we're going to model now develop a stage. From an operator view, it's already simple, right? So you get your version, your current device version, then you send a message to download and activate the new firmware image, and then you verify success. This is what an operator would do. From a system perspective, it's also not very complex, right? So your system receives a firmware upgrade request, it would validate the device information, it would validate the requested firmware information, it would validate the permissions, like does this user who is requesting the firmware update have permission to do it, and then it would send the firmware upgrade operation to the device. Process the device response, and then forward response to the user. So this is called workflow perspective on high level of how it works. And now, this is how the state machine for cyclone and over-here update to the device looks like. Again, here's the start of the state machine. So you have three states that can execute in parallel here. The first state is validating the device. So does this device exist? Do we know about it? Is the device online? Is the device connected? Can we communicate with it? The second part is validating permissions. Again, here you will imagine an interaction with a system in-house, on-prem, or a cloud system that verifies, or maybe a system like a computer that verifies whether the user has permission to execute the operations while testing. And then, of course, the metadata for the firmware is also validated in another step. So if any of these steps fail, or these tasks fail, then we go with a fail state. Next, I'm sending the get current version to the device in case you actually don't know for sure with certainty what the current version that the device has is. Right? So you will send this operation, you will track it. If you can execute the firmware update, you will move further and send the firmware update command. Once you send the firmware update command, you can go in 3 or more waiting states. I mean, here it depends on your device management protocol. So some device management protocols actually encourage their devices send progress information, right, in an event-driven way. So your device might send back an acknowledgement after it successfully downloaded the firmware, or it can send back an acknowledgement after it successfully activated the firmware. So based on how your device behaves, you can have no waiting state. It can be fire and forget. And then you have to send maybe another one to see what the state is. Or you can have this waiting state where you're waiting for interaction responses from your device saying that the operation is complete. Then you can interpret those events, and if you're effectively successful, you go to a success stage. Even if it fails again, you go to a fail stage. This is something that in the normal, we will see these executions on one of our updated devices, or one of our current devices. So the next step is an implementation example. So I actually built a prototype of this sort of state machine implementation. And the way I've done it is by using AWS services. So of course, this is not the only way to do it, but I've done it with AWS. So the component that actually starts or triggers the jobs on devices to initiate the workflow is actually implemented using IoT device management. So I've done this with IoT jobs, and the grouping and the target of the devices I've done with thing groups and the things functionality. So this is just IoT device management basically. Of course, the message parsing and the interpreting is happening via the IoT group engine, and of course, the service that groups actually together like use this standard. For the workflow management and execution, this is actually quite interesting. I've used step functions, and the reason why I've used step functions is because it is serverless, right? So I don't have to deal with the overhead of managing my own infrastructure, which was quite nice in my case. And it also orchestrates all the different executions of the state machines, right? It allows you to define your workflow, so there's a workflow definition, and it also allows you to start and sort of track the execution of your workflow. Of course, in the last slide, you will see that I have also some open source alternatives with which you can actually try and implement this architecture, which could be nice. Nice to try, in the next iteration perhaps. For state management, I'm also using DynamoDB. This is more to track information about the weighting, and I will show you this later. Device management, again, the device management service that I've used is before because it provides an intuitive broker, and of course the protocol of my choice here is MQTT. So we would have here some really slim Lambda functions that send messages on MQTT topics, and the devices respond on the default topics. And at the end of the day, my device simulations, I've written some really basic simulators, and here is where the device management protocol comes into place, right? So it's only when you're writing the device software actually that you need to worry about the device management protocol. So I've simulated a protocol called TRG69. This is the next generation modern router device protocol. So this is what the next generation modern routers probably are, using. It is an event-driven device management protocol that also allows modern routers to send back more information about the status of different operations. We'll see that connection in a bit. And the messages being sent actually in protocol encoded. So when you look on the device, you will see some protocol encoding functionality there as well. In terms of asynchronous messages, I use SMS. What the simulators are basically Lambda Docker, and this is something that we will see in the demo as well. I have the GitHub repository as well later, so I will share that here too as well. The design considerations, as you probably saw in the original architecture, we have different components with clear responsibilities, right? So we've got domain context, every component deals with its own responsibilities. The components are loosely coupled. They communicate with each other just over messages. So let's say seamless messaging happening here. And the domains are encapsulated. So retries for this particular domain are happening inside the domain and the other domain, and so is error handling. On a high level, this is AWS architecture. So I've already told you briefly the services that I use, but now you can actually see them all in action. So when you're going to trigger a firmware update operation, this is going to be IoT jobs, right? So the extra operation is implemented with Lambda. So via Lambda, I will publish a message on an IoT topic, and IoT jobs will make sure that all targeted devices are being, informed, right? Then I have a step function execution that will pick up the message from the IoT topic and will start an execution on the workflow. The workflow is, again, taking up a step function workflow, and every task has a different responsibility and will separately interact with other AWS services like the indexing service from IoT or DynamoDB. So every single time from the cloud, when you want to send a message to the device, you're not going to have your step function talk directly to your IoT device. So this is going to happen in a decoupled manner over messaging. So I use the SNS for this. And then there's a particular component that deals with message protocol encoding and message protocol encoding. So the only thing that your step function is going to receive here is an SMS message saying, hey, I finished the firmware download, or hey, I finished the firmware activation. So in this way, the components are truly coupled. So if one day I want to build my workflow management outside of set functions, I can still do this. Or if I want to build a new device management, to implement a new device management protocol outside of the ERP9, I can still do it by modifying this component only and not changing my entire architecture. Yeah. So let's skip the demo, right? So I think this is probably more interesting. So for the demo, I'm actually using a EC2 instance. And on this EC2 instance, what I'm going to do is I'm going to start about 100 of these device simulators. So what I have is, get to end. What I have is a script. Can you actually see into it? I see. That's what is displayed to all. Yeah, so these are all my components. The device simulator is running in the device agent simulator package, and here I have a very, very simple device script that will start 100 Docker containers here, and each of these Docker container is going to be simulating one device. So when this device boots up, it's going to behave like a normal device booting up and sending information about its current firmware version. So they would all be on the default firmware version because they're just starting. So they will start, they will connect to AWS IoT, to AWS IoT core, they will report their current version, and then they will just wait and remain until you reconnect it. So let's see. Let's run this. So this is going to take a while because we are dealing to 100 containers, but in the meantime, I can show you how this looks like on the cloud side. So let me get into my AWS account. So we should slowly but surely see 100 IoT things starting up and get implemented. Yeah, so honestly, right now we have 25. Yeah, we can wait a little, but in the meantime, I'll show you how these devices looks like, right? So, as I said, they are reporting the firmware version. I've given it the default version, which is 1.1. And I've also created a theme group, actually 2 theme groups. The relevant one for now, for us, is device's own firmware version. So here, the only thing I've done is put in a query where I said all devices which are on firmware version 1.1, 1.1.2 should go into this group. So we will see that this group already has, so we have 49 devices now. So they will, as they do that, they will report their firmware version, the query will kick in, and it will loop them in this thing group. Now this thing group is relevant because we're going to start our firmware update workflow against this entire thing group. So we will target all devices that are on default firmware version, and then we will bring them on another random firmware version, which is 1.2.3. This is just for testing. But of course, here you can build based on device properties, any kind of device properties that you decide to choose, you can query on and build it. So we have 75. We can take it to wait. So what will happen if I trigger my workload before all the other devices are online? What's going to happen is that some of them will fail because they will not be connected. Perhaps actually this is not a bad thing to try. Yeah, let's see. So right now, the next thing is to go to the lambda function. So you remember there's a high-level lambda function that the only thing that does is trigger the job execution on a group of devices. So the moment this lambda function gets executed, is also the logic here is not, there is no science in here. Yeah, like this would be go later and to look at this. The only thing that happens is that the job gets started, that's it. So once we do this, I don't know if all devices work online, probably not, so some of the devices might fail, let's see. Right. So we have started the actual job. So now let's go to our step function and let's see the workflows. So with rapid firmware update state machine here, so we see that we have some running workflow. So let's see when do we start this. I've got some stuff running from before. But we started and let's see 35.3. So we would have defaulted 100 executions, right? Some of them have already succeeded. So 16.3. One of them has failed. So maybe this is one of the devices that hadn't managed to actually boot up. So we can, as we have looked here, it's probably going to complain that the device was not connected. So that the device is not found. So what does it say? Yes, device is not found. So this means that the device was not yet recognized by the broker as having been fully connected. If we start looking at other state executions, some of them are still running. But once we find an execution, we can see the entire state machine that was there, right? So this is the state machine that I was talking about earlier. So the first step is getting the device, checking that the device is connected, checking that the device belongs to this same group, and then we're supposed to go and validate that we can trigger the firmware upgrade. And if the firmware upgrade can be triggered, then we can start the download operation. Now, this cycle to download operation is actually an interesting thing because here the first message to the device is being sent. So the device receives a start download command, and this state will only terminate once the actual state execution receives an acknowledgement. So even if this looks synchronous, it's actually non-synchronous, and this is the reason why there's a token here. Because the token gets issued to a dynamically table in this particular state. And when the device responds and says, yes, I have accepted the request to start the download, then the state will terminate this. So this is functionality that is provided out of step functions. It's called wait on class token. So you write the token to the database, and then afterwards, when you, on your asynchronous way back, you can look at the database for that particular token and terminate the state that had been created with that token. Then here again, you will use three waiting states. Again, messages from the device as they occur, they terminate the state. So when the device sends a transfer to repeated, this state will terminate. When it sends the operation response to the download operation, the next state will terminate. And when it reboots into the new firmware image, and the firmware is the correct one, the one that we actually wanted, this is where this state will terminate. And again, then we go into the interpreting states. And eventually we update the device. So this update thing operation, what it will do is update the ID thing with the new firmware version, the one that comes in the device reboot message, right? So when the device boots, it sends a boot message with the current firmware version. And if it's all successful, then we are going to go. I need to start up here. See if I can. Yeah, this is probably better or wrong. Then we will go to publishing state, and here in the publishing state, what will happen is that the SNS message is going to be signed. So the SNS message is going to inform the other components that actually the device has successfully finalized the firmware update. What we can also see here is we could go. You take a view, you can see all the different states. And here you can also see the input and output configuration and the definition of each of the tasks themselves. The other thing that I want to show you, let's see the status of this first. Yeah, so I think most of them have been successful, except for the one which didn't manage to put free, or two of them which didn't manage to put free. The other thing that I want to show you is what's happening behind the scenes in this, like what other AWS services, the ones that I've been talking about, are actually called behind the scenes. And it's something that we can do in this workflow manager quite simple. It seems there's this knowledge count that's trying to be put in the door and make center, and then do you. Yeah, so what you see here, each of the states that don't have the lambda hyphen are states that don't invoke Lambda function. So you can see that if the step function won't flow, there is literally no other function that gets involved. So this is all happening with the native SDK integration that step functions has with all these other services like NLDB and AWS IoT. So behind the scenes, there is a payload configuration that you're passing in, and this is actually making an SDK call, which is also quite useful because you don't have to really run Lambda functions for every functionality in your node. Right, so please don't put me afterwards if you have questions about it at all. I would like, as a last part, to actually say that in terms of further work, so the reason why we're doing this year third one is when devices different levels of constraints, one would have centralized orchestration. For further work, what I would like to enhance is open source solutions that I can build the same architecture with. So I started to look at Temporal. Temporal IO provides quite a nice orchestration service that can build similar functionality to step functions, and then maybe use observability tools like Datadog or Finite for its use. And eventually extend the device management protocols to use and then perhaps or even Mender. You see how I can integrate at device level without modifying the rest of the architecture. And this work can be also explored for other use cases like smart home automation or anything related to robotics. Here I have the link to the GitHub repository. I also have a blog post about the solution. And one thing that I found interesting, as I was doing this work, I started to read the word published blogs, and I find this blog on distributed computing very interesting. And it talks quite a lot about challenges in serverless and challenges in distributed systems. So have a look at that. I think it's great. Thank you very much for your attention. And if you'd like to connect with me, you can scan the QR code or then find me on LinkedIn or on Twitter, or you can approach me after the presentation. So now, are there any questions?
See, come.
No questions. Wow. Feeling good. Okay. Well, if you still have questions, you can ask me afterwards as well, or on LinkedIn or whatever later part. Yeah. Thanks for your attention.